So I want to talk to you about a Floquet approach to nonlinear optics in extended systems that we have been developing as part of my PhD with my supervisor, Attaccalite Grüning, and also in collaboration with David and Guy. There we go. So the linear regime or optical properties in the linear regime is very well established. Already 20 years ago, we were able to describe excitonic effects and calculate spectra in a number of experiments. But the nonlinear regime still presents some challenges with respect to the cost and complexity of the schemes involved. So on the one hand, we have perturbative methods, which one can say that it's difficult because they have to be formulated for every order specifically. And also it is not straightforward to add many body effects to it. On the other hand, non-perturbative methods are better in that they can treat all orders in the electric field simultaneously, and also they offer flexibility for the inclusion of many body effects. The problem is that they are very costly because they rely on explicit time integration. So an example of this is what we call the real-time approach. This is the work of Attaccalite Grüning, Attaccalite and nonlinear. So essentially we have an equation of motion for the periodic particle log functions. We can integrate this in time, have access to dynamical properties like the polarisation, which we can then fully transform to extract susceptibilities to any object. So one of the reasons why this is very costly is that one has to allow for a dephase in time. One has to dephase a response before sampling to extract susceptibilities. So maybe you have to run the system for 210 seconds after the introduction of the automatic perturbation, when you actually only need data in the very narrow window at the very end of the simulation, where the solution is periodic with the periodicity of the perturbation. So this brings me to the motivations of the first key message. That is, the non-perturbative methods for nonlinear optics are great in that they can treat all orders simultaneously and they are flexible for the inclusion of many body effects, but they are very costly. We want to do something about this cost. We will argue that we can address this issue with Floquet. So this is the outline. We'll divide this talk in three parts. First, we'll describe the formalism that we arrived at. We have the independent particle level, and we'll present some results. Then we will go on to show, we go on beyond the IPA approximation and show what we obtain with the inclusion of many body effects and some convergence issues that arise. And then we will try to understand those convergence issues by means of a Floquet analysis tool that we also developed. Okay, so the first part. We have the equation of motion, and the idea is instead of evolving this equation of motion until you get to the time where the solution is periodic, we can assume we are already in this regime. We can assume periodicity in the Hamiltonian and invoke Floquet's theorem. But here across the theorem, the solutions to this equation of motion will be of this form, meaning combinations of functions that have an exponential with a quasi-energy times a Floquet basis function, which is periodic with the periodicity of the perturbation. So we'll use this to construct what we call Floquet constant basis. First, we use the adiabatic approximation, so we assume there is an adiabatic evolution from one constant state to one Floquet state, so we don't need this summation here, we only take one term. Then, and this is valid only for weak fields. So we can project these Floquet states into constant states and we get a summation of the bands, and these coefficients will retain the time periodicity. And because of that, we can expand them in Fourier series, where we will get this summation of the Floquet modes, the exponentials commensurate with the frequency of the perturbation, and then the coefficients, which are the vectors in our basis that we want to solve for. Okay, so we have the equation of motion, we have the basis. Let me first say this Hamiltonian will have two parts. We have the unperturbed Hamiltonian, which will have the level of theory. This stage will only be IPA, so this will be time independent, and then the time dependent part will be the electron field coupling operator. So if you apply this basis to this equation of motion, it's easy to see that the time variable goes away, and essentially we get an eigenproblem for the quasi-energies, and this that is a quasi-energy operator, which has a diagonal part plus the electron field coupling operator. So what is left is to formulate this, or to work out this electron field coupling operator in Floquet constant basis. This is a bit cumbersome for presentation. You can check the details here in the in the publication, but I want to mention a couple of things. First, we use the very phase formulation for this operator, so it remains valid under periodic boundary conditions, and that's why we can use it for extended systems. Then this will depend on the solution of the eigenproblem, so it imposes the requirement for a self-consistent solution of this eigenproblem, which we will check on a threshold imposed on the susceptibilities we extract. And finally, just to mention, this remains time periodic as long as we use the Alliati approximation. Okay. So with this, we get to the second key message of the talk, that is, by using Floquet theory, we were able to reformulate the time evolution, time-dependent problem into a time-independent, self-consistent eigenproblem. So we implemented this into the YAML code, and we obtained the following results. So this is second harmonic generation spectra for 7 nitride and NLS2 in 2 units. So in black we have the real time, and in pink we have Floquet. And what we see essentially is that the agreement is very good. Spectra are on top of each other. At this scale, it's very difficult to distinguish between them. So good agreement between the methods. Then for bulk material, aluminum arsenide, again, very good agreement, even though we used a very small drawing in this calculation to highlight any differences, but we hardly see any. We do see some differences here at the high energy end of the spectrum, but this is actually due to conversion of the real time. So this real time calculation is done with 10 attosecond time step, and actually if we go to 2.5 attoseconds, so it's more costly, we will see that the green curve matches Floquet even more closely than black curve. Okay, so on the issue of conversions, we will briefly discuss this. The real time has two main conversions parameters. One is the total simulated time. As I say, you need to allow for rephasing time to make sure your response is properly rephased. Otherwise, some oscillations of this kind will appear in your spectrum. The other parameter is the time step for the integration, which you need to keep as low as possible to reproduce the dynamics of the system. I think if you don't, you will probably be under-converged with respect to this parameter, as is the case here in the Floquet. Okay, of course, these two choices increase the cost of the real-time calculation, and it's interesting that they don't even appear in the Floquet formalism, because it's time-independent and it doesn't rely on time integration. So what about Floquet then? Of course, we introduced the Floquet mode, so surely we need to check conversions with respect to this parameter. And what we found is very fast conversions. For second harmonic generation, for example, even at a relatively high intensity, we see that with 2, 3, and 4 Floquet modes, we get the same result. So 2 is already well converged. And then the source of the self-consistency threshold, which we need for a self-consistent solution. We use a very small value, but nonetheless, it allowed us to solve the system or converge every frequency between 3 and 6 iterations. Okay, so now that we have well-converged spectra computed by either method arriving at the same results, then we're able to compare the time it took for each one. So we define this Floquet speedup as a ratio between the times, real time over Floquet. And what we find essentially is that Floquet is between 10 and 100 times faster than the real time over a range of materials that we tested. So with this, I get to the third key message of the talk, that is that we really addressed the issue of the cost in this method. We managed to reduce it by 1 or 2 orders of magnitude, at the same time as retaining the advantages of non-perturbative methods, that is being non-perturbative in the electric field, of course, and also the flexibility for including individual effects. I mean, the flexibility is there, then we will see what convergence issues this brings about. In any case, before going into that, let me take advantage of this being non-perturbative and show you that we can also extract third harmonic generation spectra. This case for bulk silicon, again, with a good agreement between the two methods. Conversions with Floquet modes in this case is a bit more tricky. So if you are at low intensities, you will be fine with 3 Floquet modes. But if you go to higher intensities, then you will probably need 5 Floquet modes to capture fifth order contributions to the third order response, which depend on the intensity of the electric field and show up at these high intensities. This will obviously impact the efficiency of the algorithm because your matrices will be bigger and tougher to deal with. In any case, the advantage of this method with respect to the real time is still clear in the third harmonic generation case. less so for high intensity gates, but overall, when you get to gate conversions, you will get an advantage between around 10 times or even more, 50 times faster than the real time. Okay, so let's go to part 2, when we go beyond the EPA approximation and we try to include local field effects and monitoring effects. We will start with the time-dependent particle potential, and we will describe the convergence issues that this brings about. Okay, so this is our new eigen problem, our new quasi-energy operator. We will have two added terms, the particle potential and the screen exchange self-energy. And all we need to do is to work out these operators in Floquet constant basis, where we will focus for now on the particle potential. So what we do in this case is we go to the time domain and back to obtain these matrix elements in the following way. So we start in Floquet space. We have the eigenvectors saved from the previous iteration. We can use the expansion of these time-dependent states in the basis in order to recover the time-dependent states, and once we have those, we can do all that we know how to do. We can calculate the density, we can calculate the particle potential, time-dependent particle potential. We can go to constant space, and we will have these time-dependent matrix elements, which will be a periodic function of time, and for this reason, we can expand them as a Fourier series. So we can find these Fourier coefficients of each constant matrix element of the particle potential. Now it's easy to show that the matrix element in Floquet constant space at eta gamma will be this Fourier coefficient evaluated at eta minus gamma. And this is how we obtain the matrix elements for our Hamiltonian. Now, an important thing to keep in mind here is that this is not going back to the tens of thousands of time steps of the real-time approach. It's just a few points within one period that you need in order to do this, going to the time domain and back to the space. And this is why we can do this efficiently. Now, doing this on its own will bring about a lot of convergence issues. So I am already going to show you a mixing scheme that we use, the curve mixing scheme, which is a G-vector dependent mixing scheme. Effectively, it introduces a screening length in such a way that inside some screening sphere defined by this length, you have almost no mixing, and these components of the particle potential are obtained as normal with the Poisson equation in G space. Outside the sphere, these contributions, these long-range contributions, will behave mixed, and therefore will move more slowly through iterations and remain close or closer to the ground state value. So this brings stability into our calculations, as we can see here. For example, boron nitride at the TB factory level. In this direction, we're decreasing the string length, and we go from a situation where we cannot mitigate these divergences to a situation where we can. And in this case, the Floquet TD hat response is really on top of the real-time TD hat, so it matches the real-time approach nicely. Good thing to mention here is that this calculation shows a speed up of 50, and for context, the EPA analog of this calculation of this system showed a speed up of 20, so we are already seeing greater savings beyond EPA than what we saw at the EPA level. However, this doesn't always work, as I'm showing here for MOS2. I mean, we do mitigate the divergences and go from a situation where we can't to a situation where we can obtain a fully converged spectrum. However, when we get here, the spectrum doesn't match the real time so closely, and it's somewhere in between the real-time TD Hartree and the real-time EPA. And this is essentially because as you decrease the screening length, you're ignoring more and more contributions to the Hartree potential that apparently were important for the spectrum. I mean, in the limit of 0 screening length, you will recover the EPA solution, and this is more or less what is at play here. We can illustrate this by plotting in blue the deviation of the Floquet TD Hartree spectrum with respect to the real-time TD Hartree. So 0 will be real-time TD Hartree, and we can see that as we decrease the screening length, the deviation goes up towards the deviation between EPA and TD Hartree. Also, as we decrease the screening length, in green we plot the diversion frequencies, which go down, and at some point you get to 0 diversion frequencies, and you get a fully converged spectrum for all frequencies. So the idea is you reduce your string length until you get to this point, and then you see how deviated you are. And this is not too bad. For example, boron nitride, and that's how it worked. But for MOS2, we have a different situation. We need, in absolute values, far smaller splitting lengths. And at this point, well, the rich conversions, this is already deviated, and that's what we saw in the previous slide. So, for this reason, we believe this Kerker mixing scheme is not a general solution to the problems we're facing. Another things we tried that I don't have time to talk to you about, but if you're interested, you can ask me later. We tried using Padea approximants for TD-Hartree. It worked to an extent, but it wasn't better than what we already have, what I showed, so that's that. And then at the Hartree plus X level, we found even more severe instabilities in the spectrum. Overall, the key message or the conclusion of this second part is that the Floquet approach beyond beta is under development, it's work in progress. It is fully implemented, but still facing some convergence issues. Okay, so let's go to part 3, where we try to understand these shortcomings of the method, why they happen, and our approach is pretty much to solve the real time and extract the Floquet vectors from the real time, and then compare those with the ones produced by our Floquet approach. And in order to do so, we developed a tool capable of doing that, of extracting Floquet states from a real time solution. Okay, so we will use this color-coded representation of the eigenvectors. We are simply showing projections over the different Floquet modes of, in this case, the two states in the system. So the valence band will be trivially 1 here. But then through self-consistency, a state like this will gain some time dependence, which will manifest in populating these non-zero Floquet modes. So this is what we should get of resonance. At resonance, we should get something different. Still, we have this component close to 1, which we call the central component. So it's the zero Floquet mode of the valence band. But then we also have a second to largest component at conduction plus 1. So the first Floquet mode of the conduction band. And we call this the coupling component. And this is typical of resonance. So this is actually reminiscent of the quasi-inertia operator, right? Remember, we have this in the diagonal, and these matrix elements become degenerate as a function of the frequency, and the frequency matches the energy difference between these two states. Then the conduction plus 1 will reach the valence band, and we'll have what we call a Floquet cluster. And this is why you have a coupling between the zero Floquet mode of the valence band and the conduction plus 1 mode of the plus 1 mode of the conduction. Now, a key question here is to what extent do we populate this plus 1 mode here? What we found at the EPA level is that we populate, or we have values of 10 to the minus 3. And this is sort of what we would expect with the weak fields that we're using in this work. Now, at the TD-Hartree and Hartree plus X level, we don't know, because more often than not, we're not able to solve this via our Floquet code. But what we can do is we can run the real time at this level of theory, and once we have the time dependent states, do this Floquet analysis to extract the to extract the Floquet vectors. So this is what we've done. For example, at the TD-Hartree level, I'm showing here the linear response in black, so we have the peak, and then we have the coupling component that drives this response and goes up and down with the response. And what we see is that it remains in the range, in the order of magnitude of 10 to the minus 3. And the same is true for the Hartree plus X level, again, in the order of 10 to the minus 3. So, again, as I said, this is good because it's what we expect for the weak fields that we're dealing with. So let's compare what we have or what we get with our Floquet code. So let's stick with the TD-Hartree case. Anyway, what I'm showing here, it applies also to the Hartree plus X level, but let's analyze this peak of the response and perform the Floquet analysis at this stage. This is the Floquet vector we get from the real-time solutions. This is the component I was showing earlier, so this is standard, this is what we expect. And with our Floquet approach, you see that in the second and even in the 6th iteration, the Floquet eigenvectors start off well in the right direction. They really look as they should. But then at some point, by the 11th iteration, the coupling component grows up and becomes comparable in magnitude to the central component, which you can appreciate better here. We have the two components tending towards 1/2 in what would be a maximum mixing between the valence and conjugation. Of course, this high population inversion is not what we expect with fields, and it's also clear that this is preventing conversions, and this is also causing the response to diversion. So essentially, we're missing a mechanism to demote electrons from the conduction band back to the valence band, which inevitably leads us to the issue of dissipation. So this problem of the population inversion is actually not new in our code. It also showed up at the IPA level, and it can also be seen in this model Hamiltonian with two states. So it's a 6x6 matrix, 3 Floquet modes, 2 states. If we start off with this, the diagonal part of the quasi-energy operator, the eigenvectors will just be canonical. So you have here and 0 everywhere else. As soon as you incorporate even the smallest of couplings, which would be a very small off-diagonal matrix elements coupling these two modes, valence 0 and conduction +1, the eigenvector jumps straight away to 1/√2 and 1/√2. And then if you include in the diagonal an imaginary contribution, you will see that this lifts the degeneracy between the quasi-energies of this crossing and recovers the sort of eigenvectors you would expect. So essentially the valence band with some time dependence coming from the conduction. So when this problem showed at the IPA level, we solved it in this way, inspired by this. We put in this dissipation term, which is essentially a diagonal, an imaginary term in the diagonal. And this value actually controls the broadening of the spectrum. And this works at the IPA level. Every spectrum that I showed in the first part of the talk is calculated with this, matching the broadening with what we had in the data. So it works at the IPA level, but for some reason it's not enough beyond IPA to prevent these population inversions from happening. So this is pretty much where we are at with the code. As an outlook, we can say that we can investigate further the role of the dissipation operator. Maybe there's a more robust way to formulate it that can deal with these population inversions, even in the presence of local fields and monetary effects. Another option would be not to go for the broadening, but actually to work within the degenerate subspace of this crossing, where we would have a vector like this and a complementary vector, which would be pretty much the opposite. And some sort of linear combination between the two will recover the eigenvector that you actually expect. But this is something we tried, but we're not successful at. It's not trivial, I think, to define such a linear combination. Okay, so in the last minute and a half, let me show you that this Python tool, this Floquet analysis tool we developed, can also be used as an analysis tool on its own to further understand a real-time result. So, for example, we take second order explanation spectrum of hexagonal nitride, and we're going to perform this analysis at the frequency of resonance and at a resonant frequency. And what we find is this. This is an eigenvector obtained of resonance and at resonance. And what we see is that the coupling +2 component increases by a factor of 33 from off resonance to resonance. So we can really say that the component driving the response in this second order generation spectrum is a conduction +2 components. Therefore, we can track it throughout the Brillouin zone and arrive in a representation like this, where we can see which transitions make up this peak here in the second order response. We see that it happens at the high symmetry K points and also extends along the boundaries of the Brillouin zone, which is the optical gap in this direction. So this is good because, for example, it allows us to associate this second harmonization peak to the first exciton of hexagonal boron nitride, which is something that we can do based on frequencies. So this peak happens at half the frequency of the exciton, so you can say that involves some sort of process to photon resonance with that exciton, but also from this analysis we can say that the same transitions that drive this peak are also those transitions that are responsible for the first exciton of hexagonal boron nitride. And this is good because this sort of analysis comes naturally in perturbative methods, but it's not the case in real time. So it's good that with this tool we can recover this sort of analysis. Okay, so to conclude, let's recap. I started with the real-time approach, which is non-perturbative and flexible from the question of many effects, which is good, but it's very costly. So for a subset of the problems that the real-time can tackle, that is for periodically driven systems, we reformulated this as a time-independent self-consistent eigenproblem based on Floquet theory. We implemented this into the Yampa code and found out that we can reduce the computational cost by 1 or 2 orders of magnitude at the same time as keeping the main advantages of the real time. The extent to which it is flexible from the equation of many body effects is maybe debated, so it is flexible, can be included, but then it brings a lot of convergence issues that we are dealing with at the moment, and this led to tapping into the issues of population inversions and dissipation. Finally, I presented a Floquet analysis tool that is able to extract Floquet states from a real-time solution and then further analyze real-time computations. Okay, so that's been it for now. Thank you very much for your attention, and happy to take any questions.
Okay, thank you very much, Ignacio, for the nice talk. So if you have questions, please go to the reaction section and raise your hand. Okay, so there's a question by 037668.
Hi, Harian, it's me.
Claudia.
Sorry.
You always go with your code name. Okay, please ask your question.
Okay, I have a question for Ignazio. I would like to know if you think this approach, particularly the first part, can be extended to non-perturbative regime like high harmonic generation, even at the independent particle levels, or if you could be able to calculate something of this kind.
Okay, yeah, so that is tricky, I think, for 2 reasons. The most important would be that I don't know if the adiabatic approximation will hold up in the intensities or in the regime you need to obtain high harmonic generation spectra. But also, I think at a practical level, if you do higher, I mean, the size of the matrices in this formalism depend on the Floquet code. And if you need, I don't know, 12 Floquet modes or 30 Floquet modes, then your matrices will be really, really big. And I think at that point, you may be better off with the real time. So for those 2 reasons, I would think this is for the traditional linear and non-linear regime. So second harmonic generation and third harmonic generation. And beyond that, I wouldn't say from my experience that it would apply, but maybe there's a lot of things that I don't know. But that would be my take on it.
Okay. Thank you.
Thank you.
Thank you, Claudio. Nicola has a question.
Yeah, I had a question a bit related to what you just said, which is about the scaling. So you start from the real time approach, which is linear in number of electronic bands, if you want, and also linear in K point. And you replace that by a formulation, which I think, if I understood correctly, is about matrices, which makes you make it quadratic with the number of bands, and you have to multiply by the number of Floquet mode. Is it correct?
Yes. Yes, so the size of the matrix will be the number of bands times the number of Floquet modes. And you have 1 matrix for each K-point, and you diagonalize those matrices.
Okay. So it means that if I want to go to large systems, this will scale badly compared to real time, no? Or let's say differently, when do you expect that there is an advantage to use Floquet, or what would be the threshold? Have you tried that?
No, I haven't studied in particular the scaling. So I haven't tried this in big scale systems, so I wouldn't be able to respond. The analysis we did on those lines respect to the real time is really focusing on the order you want to reproduce. So in the real time, if you do real time for the second order response or even the third order response, you may be paying a high price of processing all orders at the same time when you only need the second and the third. And in those cases, there is a case for perturbative methods or for this method, which would be somewhere in between. It is non-perturbative, but the size of the matrices depend on the number of modes you want to include. So I think that there is a scope for applying this method for second and third harmonic generation, but how it scales with the number of atoms is something that we haven't tried. I mean, it is true what you say, that the matrix is, so it may become quadratic with the number of Floquet modes and also the number of bands in the system, but this is something we could try, and then I could get back to you.
Okay, thanks.
Thank you. There is a question in the comments. I don't know, Dimitri, do you want to ask the question yourself? Anyway, the question is, when will this implementation be available in the Yaml code? And which version? Okay. In the meantime, Mirta already answered, so that's
okay. Yeah, so I don't know if I'm in a position to answer that, because it's my first implementation. I don't really know how long it takes to make it from the develop to a master branch. What I can say is that probably by the end of this year, this will be, so this was first coded and then used, and now I have to do some adjustments in the code to make it more efficient and readable for other people, and that will be done in the next following months, now that I've submitted my thesis. But then from then on, I don't know how long it takes to, so at that point it will be available in the developer branch. So if somebody wants to use it, they will have to get in touch. But then how long it takes from then on to the master branch, I don't know.
Okay. I hope that answered the question of Dimitri. Claudio, do you have another question, or you?
Yes. I would like to ask Ignazio if you ever try or you ever think to use some method to diagonalize matrix faster, like Langsos, IDOC, or this technique to speed up the Floquet.
Yes. So that is actually a very good point, because when you have these matrices, the number of eigenvectors you obtained is the total number of bands times the Floquet modes times 2 plus 1. So if you have one Floquet mode, you have -1, 0, 1. So you have 3 times the number of bands, including the unoccupied bands. But actually, the eigenvectors you need, it's only the occupied ones. So maybe you have 4 occupied bands and you need 4 eigenvectors. In the case of external and polarization, you need 4 eigenvectors, and you're obtaining, I think, something like 56 eigenvectors. So of course, there is scope to accelerate this method by avoiding full diagonalization and doing some Lang's method, or even some variational approaches that are out there in the literature. And this is something that we have in mind, but not something that we were able to try so far, because already as it is, it shows an improvement reflected in the time. But yeah, that's a good point.
Okay, thank you.
Thanks.
Thank you. So the main problem seems to be to include these many body effects in a stable way.
Yeah.
And so in the end, you said something about that you had a similar problem in the IPA, but that can be solved with this, including this dissipation term.
Yeah.
It was not clear to me, but maybe also not to you, I don't know. Why then it doesn't work in the many body case? So why does it work in the IPA?
So I think there's grounds to believe that when you have excitonic effects, or even with the local fields, the basis, or the independent particle basis you're using is not really more fit for purpose any longer, because all your states are shifting, and that is probably a reason why this isn't working. And one idea would be to start with an excitonic Hamiltonian or an electron hole basis instead of a constant basis. So that would be an option. Another option would be the idea that this becomes ill-conditioned when you have many body effects. So small changes in the operator lead to big changes, which for a self-consistent solution is really the worst you can have. So that could be another reason why it breaks down when you include the effects, and you have to do a careful management of these divergences. But we are investigating it, and of course, any suggestions are always welcome.
And can you determine whether the problem is ill-conditioned or not? Is it simple to do?
I don't know how that would be done mathematically. So I mean, there is reasons to believe that because you have a situation that is sort of similar to the DFT case with the charge lodging problem, where you have very small difference in the density causing very huge differences in the charge potential and then feeding into the cycle. But I disclose that I don't know mathematically how we would have to do to determine whether this is a condition or not. But this is a problem that is talked about in the literature, for example, for strong hybrid methods as well.
Okay. So maybe Mirta wants to comment or ask a question.
No, yeah, I think that the difference could be that in the IPA, you have basically, it's almost diagonal because it is in that IPA basis. And when we add the dissipation, it's a sort of diagonal preconditioning of the matrix, which is helping, while with the when we add some coupling due to R3 and even more with Bethe-Salpeter, then I think that one would need some, in terms of preconditioning, some off-diagonal preconditioning. And regarding the ill condition, yeah, there are a mathematical way to check the ill conditioning of the matrix. So it's something that we can definitely do next to see if this, I believe that is the problem, that when we are close to excitation, there are the matrix became ill conditioned and cause all this problem. And then when there are strong couplings, the simple preconditioning, diagonal preconditioning from the dissipation is not working as it's working for the independent particle case.
Okay. So let's maybe go to Nicola. You have another question? And then Claudio, if he has another.
Yeah. So it's a bit related to that. So it's more a conceptual question for me. So when you have independent particle, your Hamiltonian is indeed periodic in time, so there is no problem to apply Floquet theory. But as soon as you put interaction, you are not periodic in time anymore because you have the functional dependence. Even if you think about the R3 term, if you have a system with a periodic driver, you will still excite carriers every half cycle of your laser. So you will change every half cycle you will change slightly the density. And this creates a problem that the interaction makes the applicability, at least for me, it's a conceptual problem I always have with interacting effective Hamiltonians and Floquet. What do you think about that? Could it be also creating problems, especially at resonances, because you do excite, say, carriers in your time evolution? So basically, you break the periodicity, and the applicability of Floquet goes away. Or I don't know. Maybe I'm wrong, but
no. I mean that is of course a central point here, and it's been studied. There's a 2013 paper, I think, a PRA paper by Kapoor is the author, where they studied this at the TDFT level, and they concluded in general the exchange. So they do it for TDFT, but I think that the similar things apply to Hartree. Mm-hmm. The exchange correlation potential, even in the adiabatic LDA, is in general non-periodic because the density is in general non-periodic. Yeah. But within the adiabatic approximation, which I showed, which is just using one Floquet mode rather than a superposition of Floquet modes for each state, you can recover a periodic density. And that's what they do, and they show that this remains valid to, I think it was 10 to the 14th kilowatt per centimeter square. So it remains valid for fields beyond what we're using here. Of course, this is system dependent, but we believe that for the fields we're using here, this should hold up, and we should have a periodic density. But of course, it is obviously an important point whenever you're trying to apply Floquet to this sort of Hamiltonians. We believe we are covered by the adiabatic approximation, but I mean, could be the case, but we aren't.
Okay, thanks.
Thank you.
Claudio, a third question or comment? Oh, he's gone.
Maybe he had the hand up from the previous one.
Yeah, probably. Okay. And okay, we can check on him because he has the black screen. Okay. Are there any other questions or comments? I don't see any, so maybe this is a good moment to thank Ignacio again for the nice seminar. Thank you for the discussion.
Thank you. Thank you for listening.
Thank you very much, and see you next time after summer probably.